Hello, my name is Tong Jing and I will be discussing the topic of ordinary differential equation, also known as ODEs. First off, let's take a look at the concepts and historical development of ODEs. Let's start with the basic concepts. ODEs involve the derivative of both independent and dependent variables and express relationship between rates of change. They come in various types, including first-order and second-order ODEs, as well as linear and non-linear ODEs. Now, let's take a look at the history of ODEs. The development of ODEs began in the 1680s, spearheaded by brilliant minds like Leibniz, the Bernoulli brothers, and Newton that laid the foundation for this mathematical field. Moving into the 18th century, the school of ODEs expanded to include partial differential equations, with figures like Euler, Bernoulli, Lagrange, and Laplace making major contributions. In the 19th century, mathematicians like Cauchy applied ODEs to heat, optics, electricity, and magnetism. The 20th century saw many advancements of ODE that were influenced by set theory and topology, with the addition of people like Poincare applying ODEs to quantum mechanics and relativity, showcasing their broad applicability in modern science. Next up, let's explore the various methods for solving first-order ordinary differential equations, or ODEs. This flowchart will guide us through the different approaches based on the type of ODE we encounter. First, we need to determine if the ODE is linear. If it's linear, it can be either homogeneous or non-homogeneous. For a homogeneous linear ODE, we can solve it using a straightforward formula. While for a non-homogeneous linear ODE, we use an integrating factor to simplify the equation, allowing us to integrate and find the solution. If the ODE is not linear, we ask how it looks. If it is separable, we can isolate the variables on the opposite side and integrate each side separately. If it is an exact differential equation, we check if it satisfies the condition for exactness. If it is exact, we can solve it directly. If not, we look for an integrating factor that makes it exact and then solve it. For Bernoulli's equation, we use a substitution to transform it into a linear ODE, which we can then solve using linear methods. Finally, if the ODE is not exact and doesn't fit any of the simpler forms, we use the integrating factor method to simplify and solve the equation. To simulate the real-life application of ODE, let's model a case study that is about pollutant in a lake as seen on screen. To solve the problem, let's start by gathering some information about the lake, like its inflow and outflow rate and its natural degradation rate. Combining this factor, a differential equation representing these processes can be formed. Next, we can solve this equation using the integrating factor method. We first choose an integrating factor that simplifies the equation. Multiplying our differential equation by this integrating factor allows us to express it as the derivative of a product. We then integrate both sides with respect to time, which gives us a new expression involving the pollutant concentration. To find the particular solution, we can use the initial condition that gives us the pollutant concentration at time 0. This allows us to determine the constant in our solution. Ultimately, we find the expression for the pollutant concentration over time, showing how it decreases due to both the outflow and natural degradation. These are the references used in this video.